The subject is air-to-air tracking of a target, which may or may not be a target in a military sense, whether by radar or for use in air traffic control by sharing satellite navigation data. Here we'll consider a challenging scenario with two aircraft both flying at 1,000 feet per second, but in opposite directions on parallel paths 1,000 feet apart. This present image depicts their instantaneous locations at some time before they would reach their closest approach, but they start from positions separated by a much larger distance, more than 16,000 feet apart. The dynamics can be understood from the little symbolic sequence shown next. A short clip, not to scale either spatially or in time, and not fancy, just a little sketch of a sequence, will now begin from that starting position with the two aircraft more than 3 miles apart as the radar at instantaneous location O keeps its antenna beam, depicted by a dashed line, pointed toward a target at X. Distance between them is getting smaller, closing, 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 closing. Then it's opening, distance between getting larger, opening more, more, continuing to open, and it will just keep on opening. For safety of air traffic control, cases like this with lower speeds but similar geometry clearly require accurate monitoring of relative dynamics between aircraft. There's no way for this video to allow nearly enough time to cover all the work I've done on this, writing both formulations and programs subsequently validated with flight test data. The flight test conducted at Ohio University under the direction of Professor Martin Udhag is among the most important of those programs described in the link shown here. GPS measurements, as described in the link just shown, were shared across the same data link used for ADSB. The test included an even more severe flyby, a crossing scenario, 0 horizontal separation at closest approach, with separation in altitude only. The crossing is shown along with its accuracy results, RMS values below a centimeter per second for deviation of measurements from their anticipated values. Opportunity offered by that flight-validated carrier phase sharing will be revisited at the end of this presentation. But right now we'll revisit the parallel paths depicted in the little video clip for measurements from radar. Let me first note here that two antennas with a little overlap would then be needed to maintain that track operation. The antenna covering the region colored red in this sketch would be used at first, and somewhere near halfway through, the other one would be switched in. Everything would be coordinated, so there's no need to be distracted by that. Our focus here is on what happens in the track file, which the radar updates every 1/10 of a second in the sequence that was just displayed. At every update, the radar receives an indication of the target's instantaneous location relative to its own instantaneous position. In the two-dimensional image used here, that consists of range, distance, and sightline direction from O to X. In this scene, that direction expresses how far, left or right, azimuth, that sightline is relative to the radar's straight-ahead bore sight. In a three-dimensional view, the full direction would also include elevation for the target being above or below. Once again, I'll digress briefly to note how the antenna direction depends on antenna steering relative to the airframe and also the orientation of the aircraft carrying it, while that aircraft itself is rotating. so the instantaneous sightline direction involves more than one set of trig computations. As before, we just note that all direction-related considerations can be taken into account by well-known standard methods, with everything being coordinated. One last digression. Doppler is not discussed here for two reasons. It isn't always trustworthy, and it isn't needed since we have sequences of range data. Okay, now we can return to describing the tracking operation. In the scenario used, there are 167 updates centered around the 84th point where range rate is 0. Radar engineers will say, hey, both altitude line and main beam clutter are there. That's correct, but even before or after that, the numbers I'll show you are so extreme that the conclusion to be reached is inescapable. Let's review that 0 crossing when range changed from closing, decreasing, to opening, increasing. It happens when the two aircraft are instantaneously beside each other, just 1,000 feet apart. I'll save you the trouble of calculating the rates at the 83rd and 85th points. Each is a little over 392 feet per second, one positive and the other negative. Then subtracting those two values and dividing by the time interval between them, 0.2 of a second, or if we perform the calculations using vector analysis, we get essentially the same answer, 3,922 foot per second. A range tracker sees that as range acceleration, second derivative of range. It exceeds 120 Gs. No range tracker is able to follow those dynamics. In other words, what was for years the accepted way to track would not be adequate for this scenario. That's why in the early 1970s, I chose a different approach to be described shortly. The plots shown now aren't essential for all viewers here, but some will want to see the time history of range, upper right, range rate, evaluated by the two different ways on the left side, and range acceleration at the lower right. The plots are included here just for those interested. Other scenarios would give less extreme results, but less extreme than 120 G doesn't give much reassurance. The point is that a conventional range tracker will be challenged to maintain continuity at close ranges where sight lines rotate fast. You have just witnessed the effect of centripetal acceleration, which is just an abstraction that arises from tracking in a rotating coordinate frame. To show it's no exaggeration calling it just an abstraction, consider how much real acceleration is there? Negligible. Both aircraft are striving to hold constant velocity. That alone would justify my decision to relinquish tracking in the line-of-sight coordinate frame. Let me assure you this is no minor issue. Range and angle track belong to the history of old analog mechanization. Once computer control of radars became feasible, it became a no-brainer to characterize track states in a coordinate frame with very little rotation. Specifically, in the 1970s, I chose the frame used for the inertial nav reference. That choice offered so many additional benefits, it was no contest. The sources cited here contain pertinent formulations and explanations. Here I show an exaggerated amount of angle offset above and below a dashed line representing the radar's perception of the tracked object's direction. Relative strength of the return from up and down, or left and right, is used to correct that perception. Simultaneous squints give accurate corrections. Without a monopulse antenna, though, sequential changes in amplitude are allowed to confuse those comparisons. Scintillation then severely degrades the estimated velocity, giving it plus or minus 500 foot per second in the example shown here for a span of 1,000 feet per second. About all you can do then is low-pass filter the display commands. That makes the display less distracting, but it won't eliminate the real problem. Use a monopulse antenna. Earlier in this presentation, I noted that flight test results with updates from GPS produced residuals supporting centimeter per second RMS velocity accuracy in all three directions. That is dramatically better than any performance promised by ADSB. Safety is the reason why this is so important. Instead of urgent, and therefore violent, climb-dive maneuvers from TCAS, collision avoidance should be enabled by moderate adjustments in horizontal velocity, well in advance of closest approach. In-depth coverage of that topic is included in a recent SAE International report advocating major changes in air traffic management. The link shown offers a 2.5-minute video introducing the recommendations put together with a team of eminently qualified contributors. Although coronavirus now makes airspace less crowded, urgency can quickly emerge from either resumption of increase in air traffic or proliferation of unmanned systems in the airspace.